All right. Now that we've kind of finished our discussion of ARIMA modeling, I'm going to talk about one way we can kind of tweak um, or maybe build upon, I guess it's a better way of saying it, a way we could build upon ARIMA modeling to kind of model some maybe a little bit more realistic real life situations. And in particular, we're going to talk about something called an intervention model. So there's actually two types of intervention models. We'll look in a little bit more depth in each of these in just a second. We have step functions and impulse functions. Um, Both of these are used to model situations where a drastic singular event alters the behavior of a time series, right? So something like a strike, something like a war, a famine, a pandemic, um, right? These are all these kind of like massive disruptive events that can sometimes permanently, sometimes temporarily, right, change like the pattern of whatever time series we're following, right? The difference between a step function and an impulse function, a step function is we model this as like a permanent change. The impulse function is we measure it as a temporary change. Yeah, so here we go. Step functions. In the situation of a step function, the event permanently alters the course of a time series. We can model this by including a dummy variable, let's call it S, that equals 0 up to the event and 1 after the event. So, right, in this case, S is what? S is modeling the permanent loss or gain due to the event. So examples might be a change in a company's policy. That's actually the example we're going to work with in just a little bit. A forest fire, or some sort of permanent government intervention like a smoking ban, for example. Impulse functions are where we have a temporary short-term effect, and we model this by having a dummy variable that's equal to 0 up to the event, 1 for some period of time, and then 0 from that point on, right? So instead of being 1 all the way to infinity, it's just 1 for some short period of time and then goes back to 0. And so here S represents the temporary gain or loss due to the event. And so examples of situations where we might include an impulse function um, would be like short-term policies or interventions, government rebate checks, strikes. And we could also actually use these functions in an interesting way. I don't know that we'll have time to talk about it this particular lecture, but these functions could be used in some interesting ways to compensate or adjust for outliers, right? We could model these outliers essentially as impulses. Again, we're just kind of getting like a little bit of exposure. Really what motivated me to put this together, and I don't expect anyone to do this for your projects or anything, but we have had the misfortune of living through a globally disruptive event, and depending on the time series that you've picked, right, you may or may not see some sort of very dramatic disruption that coincides with the start of the pandemic. And in this case, I kind of go back and forth, but I suspect that the pandemics maybe more accurately modeled with an impulse function rather than a step function. I know in some things are kind of like returning to normal, but we don't really have a clear-cut time as to like when it is over. Unlike a strike, for example, like we might use an impulse function for a strike. Strike has a definitive start date, has a definitive end date. That's not the case for the pandemic. So my thought is a step function is probably most appropriate. So for those of you that want to play around with it, not required for your projects, but I do suspect some of you might have this kind of pattern in your data. And if you wanted to kind of think about how you might model it, this would be the way that it's traditionally done. So just getting us some exposure. There are more complicated models out there, right? So in this case, we're modeling with that dummy variable. We're modeling like dramatic, almost instantaneous, like gains or losses. There are ways of kind of improving our intervention model by adding parameters where that increase or gain is like a little bit more gradual. So that would be kind of like the next level up from what we're talking about here. Now, how do we do an intervention model? An intervention model is really just a special case of regression models, and we talked about that. We talked about that recently. We talked about how we can use ARIMA modeling to model the errors within a more standard 512 type regression model. And intervention models are really just a special case of that. So the basic process to build an intervention model works like this. So you find an ARIMA model that describes your largest section of uninterrupted time series, right? So do you have more time before or after your disruptive event? We're gonna take whatever larger chunk we have, and we're gonna try to model what the overall relationship looked like. Our assumption is going to be that that relationship is the same in both pieces. We just need to connect them with that dummy variable that models like the increase or decline. So we're going to fit an ARIMA model to the largest section of our uninterrupted time series, right? The section that does not include our dummy variable, or doesn't overlap with the dummy variable, I should say. Then using our appropriately defined dummy variables, right? It's a little different depending on whether we're doing a step function or an impulse function. We're going to fit a regression model that describes the intervention. We're going to modify that regression model in the following way, and there's a little bit of theory kind of why we would do this. We're going to apply differences to our dummy variables based on any differences that we needed to do in our ARIMA model from step one. So any of those differencing transformations that we had to do in step one, we also apply those to our Y variable. We also apply those to our dummy variable S. And then finally, we take that ARIMA model that we found in step one and we fit it to the error terms. Okay. So pretty straightforward, right? We've been gradually learning how to do all these different things, so we're gonna see how to bring it together. And we are getting a sense like this is still a pretty basic model, but there is a lot going on, and that's where I've said like moving from ARIMA models to like the next level of models is like a pretty big jump in complexity. So here's a real life example, although admittedly a little bit dated. It's based off a data set that looked at the monthly, so it's monthly data, monthly average directory assistant calls. So you may or may not remember this, may or may not be part of your frame of life. I remember it. It was a thing when I was a kid. There was something called 411 directory assistance. You could just like pull out your phone and you'd hit 411 and it would ring and some person would answer it, and then you would say like, I want to know the phone number of Joe Smith, and they would look it up for you, and they'd say, oh yeah, Joe Smith's phone number is this. I guess probably, I mean, you could use it for people, but I think maybe more often you'd say, I want to know the phone number for the movie theater, I want to know the phone number for the hardware store, right? This is sort of pre-internet. And I guess we did have phone books back then, but I don't know, maybe phone books were outdated at some point. I don't know. We had this 411 thing, and sometimes people would use it. And I guess at some point so many people were using it, they wanted to discourage people from using it. And so they added a fee. That is, if you called 411, like, you had to pay a little bit extra in your phone bill that month. So it used to be free. So we have data from January 1962. It was free all the way to 1974. So that's like 12 years of free data. And then from 74 to 76, this fee was added. And so we have like 2 years of data where it cost money to use this directory assistance. And look at that, right? This is a pretty classic pattern for when we would want to use an intervention. Right? We see maybe why they decided to initiate the fee, right? We could see the number of 411 calls going up and up and up and up. I guess at some point it was too much and they decided they needed to curb it. So they initiated these fees, and maybe as expected, perhaps maybe more than expected, right? There was a pretty dramatic drop in the number of calls once it actually cost money to make them. All right, so let's go ahead and set up our intervention model. First thing I need to do is I need to create that dummy variable. So, right, I worked out the times. What was it, like 1974, 1960, 1974? So basically time 1 through 146 is pre-fee. So that's going to be our dummy variable of 0. Anything from 147 on, that's going to be after the fee was implemented. That's going to be a dummy variable of 1. Okay. And then remember, our first step is going to be what? It's going to be to fit a ARIMA model to the largest part of our data that's uninterrupted. So, right, in this case, what do we have? We had like 12 years before the fee and 2 years after. So in this case, our largest chunk of data is that 12 years. So I'm creating a subset, right, of the data, which is basically just everywhere where my dummy variable is 0. That's going to be all the data before the fee was implemented. And then I'm going to use that subset data set to build my ARIMA model. Yeah, so let's go ahead and do that. Let's fit a model to the subsetted data. So here's the plot of it. We could actually see, right, so this is before the fee was implemented, and we could see, I guess, just even like just knowing that fee was coming was starting to like reduce the calls a little bit already. But we are missing the most dramatic part of that plunge, and that would be the month right after this. All right. So step one is we need to get stationary data. So we could start by taking a first simple difference. Now, it's always tricky when you have seasonal data, because I do this and I don't know, it maybe doesn't look too bad to me, to be honest. That is, it looks like it's fluctuating reasonably along a horizontal line. It looks like a few spikes at the end there, but the bulk of the data looks like a reasonably constant variance. However, sometimes it's hard for the eye to coax out seasonal patterns, which is why when I have seasonal data, I do encourage you to look at the SAC. So let's go ahead and do that in the next slide. I look at the SAC and I see a big spike at 12, a big spike at 24, a big spike at 36. If I were to zoom it out more, I would see another big spike at 48 and 60. That is, my seasonal lags are not dying down quickly, and that's indicative of my data not being stationary. So the simple difference by itself is not sufficient. So what should I do next? I'm going to look at just the seasonal difference. So here's a seasonal difference. It doesn't look good, right? It looks like, I guess, maybe fluctuating around a straight line, but then it drops and then it climbs and then a straight line and then it drops. That is, I still kind of have this like just up and down drift. So the first simple difference wasn't enough. The first seasonal difference was not enough. Let's try both of them together. And so this looks pretty good to me, right? It's fluctuating along a straight line. For the most part, looks like a constant variance, kind of like before. I do have like a little bit of spikes at the end. Like I guess really just 2 spikes. but the bulk of the data, it looks like reasonably constant variance. So I feel pretty good about this transformation in terms of achieving stationarity. So here's my SAC and my SPAC. And so what are we going to conclude? Well, let's start with the non-seasonal level. And if you want, you could pause this slide and try to figure out the seasonal and non-seasonal by yourself. I look at the non-seasonal level, and what do I see? I don't see a spike at time 1 or 2 or 3 or 4. I don't really see any non-seasonal spikes. That tells me I do not need a non-seasonal model. That's pretty straightforward. What about at the seasonal level? Well, I see a big spike at 12 for both the SAC and the SPAC. Okay. And then I look, and it's a little hard to see exactly where it's lining up in terms of the 24, where that 24 is at. But I think in the SPAC, the 24 is actually that block where there's like pretty much like nothing. There are two kind of larger bars around it. And in general, looking from 12 to 24, well, let's focus on the 24. So what does it look like? It looks like both of the bars cut off, as it often does. But we know that there is no such pattern where both of the bars cut off. So we have to try to determine which one's cutting off more and assume the other one's dying down. Now, to me, this is like, it feels like a coin flip to me, to be honest. But like I said, I think the 24 lines up. I believe I tested this earlier with like basically like a bar that's like almost so flat it's like non-existent. And so that's why I decided that I thought the SPAC cut off more. If you said that the SAC cut off more, that's a reasonable conclusion as well. How could we sort of compare these things? Well, we could fit a seasonal model of moving average order 1, a seasonal model of autoregressive order 1, and we can compare their BICs and try to pick between them that way. All right, so no need to overthink it. I'm going to go with the SPAC cutting off more. That implies a seasonal autoregressive model of order 1. Oh, sorry. No, I went with the SAC. I apologize. So yeah, that's how much of a coin toss it was, as I've already forgot what I had decided. So a simple and seasonal difference we already saw was needed to get stationarity. We saw no spikes at the non-seasonal level. That was pretty straightforward, easily visible, meaning that we don't need a non-seasonal ARIMA model. At the seasonal level, both SAC and SPAC seem to cut off, but we know that's not possible. And so here I contradict myself. Sorry about that. It looks like the SAC cuts off a bit more. And so here I'm suggesting a seasonal moving average model of order 1. Again, I would probably in this case do both of them. This example, the goal is the intervention model, less so the ARIMA model. So I'm not getting too crazy with it. But again, if I wanted to be comprehensive, I could test both of those models and use the BIC to see the preferable one. For now, let's go with the seasonal moving average model of order 1. All right, so now we got to do steps 2 and 3. So steps 2 and 3, you actually can do intervention models in the time series forecasting system, but I find it a little bit easier, and I'm more confident doing it in PROC-ARIMA. So let's go ahead and look at that. Plus, PROC-ARIMA is how I showed us how to do these regression models already. All right, so here it is. Right, I use PROC-ARIMA. We said we want the first simple difference and the first seasonal difference. So that's why I do y 1, 12. That's doing the differencing. The cross-course statement is specifying any covariates I want to bring into my model, as well as any differencing. And remember, we said that we're supposed to difference those the same way we had to difference our ARIMA model. So that's also going to be 1, 12. We wanted what? So now we got to build our model. We wanted a seasonal moving average model of order 1. So that's lag 12 and just lag 12. So I do parentheses 12. And I use the input equals S. That's basically going to do what? That's going to build a regression model of Y equal S, where Y and S have been differenced appropriately, and the errors are fit, the epsilons are fit to that moving average model of order capital Q equals 1. And then I picked 12, so let's forecast a year out. Forecast lead equals 12. And so here's our model, right? So we see here that the y-intercept is not significant. We could remove if we wanted to, not a big deal either way. We have our estimate for theta, and that's highly significant. We also have, where it says num1, that's our estimate for our dummy variable. So our dummy variable is highly significant. It's estimated to be negative 398, if I do a little rounding, negative 398, which is saying what? So like here I'm quantifying something maybe important. It's basically saying that when we implemented the fees, there was a drop, a permanent drop on average of about 398, I forget what the units were, 100 or 1,000 calls to directory assistance, right? So that's the nice thing about using these regression models is I have these coefficients I can interpret just like I did in 512. Here's my my correlation matrix. So I want to make sure none of my correlations are too strong. In this case, the correlations are actually quite small, which is indicative of a good model. And here are my LBOC scores. All of their p-values are well above 0.05, indicating that our model addresses the dependency appropriately. And that's basically it, right? So I fit my model pretty well. Unfortunately, when I use Procurema, it takes a little bit of work to actually plot it out and see how well my estimates are chasing the data, but they are chasing it well, I assure you. And you know, with some outputting and stuff, we could do that. But yeah, this is it. It's our intervention model. We fit our dummy variable. A dummy variable gave us a little bit of insight into the problem. I didn't show us the forecast, but we have made appropriate forecasts 1 year into the future that continues the ARIMA trend after taking into account the drop due to the implemented fee. All right. And that right there is intervention models, or at least an introduction to intervention models in a nutshell.